All right, in this lesson, we're going to talk briefly about finding roots using a graphical method. So the first question that we have is that, what is a root? And so a root is going to be when we have any function of a single variable in this case. And it's going to be the values of x. So it's x when the function of x is equal to 0. And so we call these the zeros of the equation or the roots. And so, for example, if we have a function of x where we have ax squared plus bx plus c, then we can easily see what these zeros are because we've all memorized the quadratic formula. We have two roots here where we have our first root is negative b plus the square root of b squared minus 4ac all over 2a, and then our second root is going to be negative b minus the square root of b squared minus 4ac all over 2a. And this is one instance in which with this quadratic polynomial we have an analytic solution that we have memorized this formula for. But then the question is, what if we just have some data, and perhaps it's not an analytic data, it's not a well-known function, but it is a function of x. And it's when these data don't have a formula per se that we would need to use numerical techniques to locate those roots. So let's move on to what is going to be the basics of root finding, is that if we're given some data, everything of course needing to be a function of x, then if we're going to find the roots, we can see here that our roots are located here and here where they cross 0. So we have an x1 and an x2. And so just a piece of advice that I want to give you whenever finding roots using any method is always plot the data. This is what we have, particularly in MATLAB, a tool at our disposal to be able to indicate, well, where should that x1 roughly be, where should that x2 roughly be when given a particular function across a particular domain. And so given this, the most simple way that we can think about finding roots is going to be graphing it and then zooming in on a particular part and visually inspecting to find out where this x1 lies on the x-axis. Let's do that in MATLAB with the function f of x is equal to sine of 10x plus cosine of 3x. And we'll do that where we have the domain x is between 3 and 6. So let's plot those data by first defining our x using our linspace. We're going to go 3 to 6. We'll put 50 points in there. And then our function of this will be sine 10 times x plus cosine 3 times x. We'll generate a new figure, and then we'll plot x versus y. All right, you see that we get this nice plot between 3 and 6. Here is our domain. This is a sine function and a cosine function stacked on top of each other. And as we're looking here, let's count these roots. So 1, 2, here's my 0. 1 root, here's our second root. We get a third root. Here we may or may not have a root. So we could say 4 and 5, not really sure. But 4 maybe here, 5, 6, 7. So do we have 7 roots? Do we have 8 or 9 roots? It's a little bit hard to tell. So this is where the grid on function really helps out a lot. So place your grid on. Let's run this again. And then here, we're still having a little bit of trouble right here seeing about this. But it appears that if we use our zoom tool, using this, we don't drop below 0. But in general, by looking at this plot, we get to count the number of roots that are here, and that would be the first step in a graphical method. The next part is going to be to zoom in to, let's say, the first root, finding where it crosses 0, And then looking at the x-axis, and so we see that it crosses 0 between 3.27 and 3.275. And so this means that we know our root to at least one decimal place. We could continue zooming in a little bit further. And here's our point. And we see that we are at 3.27214 and 3.27216. So now we have this narrowed down to 3 decimal places. So we can say that our root is located at 3.272. Let's write that down, 3.272. And we could, if we want one more decimal place, we can continue to zoom in. So now we have it to 4 decimal places. 3.2721 is on the left-hand side of the 0, and 3.2721 is on the right-hand side of the 0. So to 4 decimal places, this is what we have. Well, let's go back to those roots that were a little bit difficult to see on whether we even have a root around here. Now, one of the things that we see here is that our local minimum didn't cross 0 the way that we have it plotted. Now, we can improve that by going back to our code and changing the number of points that we have. So let's put in 100, run it, and then use our zoom tool and locate our first root. And it looks like we're crossing 0 right at 4.235. So this is root 4, 4.235. And that we can even say here that we didn't see it cross 0 before. It crosses 0 now 2 times. But we do have a problem in that this still looks pretty choppy. So we can increase our resolution again in our lens space. Going back to our function again, let's examine those roots. And this looks much smoother now. So we should get a better approximation of where the 0 is. Continue to zoom in on where the 0 is. So 4.229 and 4.2295. We'll zoom in one more time. And 4.2291, 4.2292. Let's keep on going. Let's get that 4th decimal place. So 4.2291, 4.2291. Now we've refined this, and so we're going to say it's no longer 4.235, but 4.2291 when we've increased our resolution to 1,000 data points between 3 and 6 instead of the 50. So when using a graphical method, I want to note that the resolution of your x-axis, the horizontal axis, matters greatly in coming up with a good approximation for your roots. And we can see that here because we did in our lens space, there were 50 points in the domain. And here we used 1,000 points in the domain. Now, using a graphical method like this can be incredibly cumbersome, especially as we're looking for 1, 2, 3, 4, 5, 6, 7, 8, 9 different roots just within this domain. So if we're zooming in, attempting to visually inspect and find that point, and then doing this 9 times, it just, like I said, it gets really cumbersome, and this is another reason why a numerical method is going to be helpful. And many of you should be asking the question right now, well, doesn't MATLAB already provide a function to perform this root finding application? And so the answer is yes, it does. It's called fzero. So let's do fzero and figure out how to work this. And once we see how the fzero function works, we're really going to be recreating different portions of this over the next few days as we look at bracketing method and fixed point iteration and so forth. But let's see what's happening here. Fzero is a single variable nonlinear zero finding function. And so the syntax for it is going to be x is equal to f0, And the input into the built-in function is fun. We'll talk about that in a second. And then x0. And so we're finding the zero of a function, and this is for a single, you're going to find a single zero, and it's going to be near the value x0. And so that's why it's really important to plot the function that you're finding the roots on, because if I want to find the root that we said just a moment ago is equal to 4.2291, then essentially I need to give it a guess. And so the guess that I'm going to give it in this fzero built-in function should be somewhere near 4.2. And so let's investigate that. Let's do that by using the fzero function. So I like to copy and paste my syntax in which we're looking here for the root. We're going to use the fzero function. And then for this fun input, this fun is a function handle. So to have a handle, this is a way of calling a function as an object or inserting a function into another function. We have to use the handle operator. So that means first we need to have a function. So let's define the function that we're going to use, and we'll do this as a subfunction. So function and end, and I'm going to call this example function. And this needs to have an input of x and an output of y, because we're talking about a single variable function. And the function that we want to use is going to be the sine of 10x plus cosine of 3x. And now that we have created this subfunction called example function, to insert this here, we can't simply put the function name, but we have to use the @ symbol. And the @ symbol is saying this is a function that I'm putting inside of a function, and we're saying get the handle of the function, which is a simple way or a rough way or loose way of saying that we're treating this function as an object itself that we're putting into another function. And so then we need to take a guess for something in the ballpark. And if we look at our plot here, okay, here's our minimum. Let's take a guess that it's maybe 4 of where it's going to cross here. Or, yeah, let's put 4 in. And let's find out what comes out as our root. So this is kind of interesting. Even though we chose a point that's 4, and you would think, well, this should be the closest root to it. It's on this side of the slope. It gave us that the root is 3.7457. And if we zoom in here, we should see that the root is indeed 3.7457. But what it's telling us is that we didn't get close enough in our guess. So let's try 4.1 instead. And so even with 4.1, we get the same root. It's finding the same root, 3.7457. We're not getting close enough. So let's try 4.2. 4.2 puts us firmly, this is definitely the closer root. Puts us firmly on the downslope. We are still getting 3.7457. So even though we're using our example function, we're putting in 4.2, we're still not getting the one that we want, which should be 4.2291, somewhere in there. So let's see if we can get it any closer. 4.22, and we're still getting 3.7. Let's try another one. 4.229. And so it looks to me like we're going to have to zoom in and get a point that's on the right-hand side of this function. So let's put in, or the right-hand side of this 0, so let's put in 4.26. And we finally get our root of 4.2291. So So one of the first things I want you to see is that when using the fzero function, the fzero command, it's using a numerical algorithm that is very sensitive to the input. So it is incredibly important that you put the correct input in there to get that output out that you're expecting. So another way that we can do this is by, instead of putting a single input in, by putting two inputs in. And so, for example, if we want to get this 4.2291 that we were looking for before, we can, as our inputs, put in 4.1, and let's just say 4.3. And then by putting in 4.1 and 4.3, we just got an error. And here's why we just got that error. So 4.1 is on the left side of where the 0 is. 4.3 is on the right-hand side of where the 0 is. And so this interval itself, it contains two zeros. But the error that it gave us is that the function values at the interval endpoints must differ in sign. So that tips its hand as to how it's looking for where the zeros exist. It's looking for a change in sign between the positive and the negative, and in this case, for their 0 here, between the negative and the positive. And so we're going to be employing that tomorrow, or in our next lesson, and this is what's called a bracket method. And you can see that we put them in between brackets, 4.1 and 4.3. If we change that to 4.26, putting our brackets between 4.1 and then 4.26 here, truly surrounding that single 0 that we have, then we should get 4.2291 as the root of the equation. And so the main point that I want to use here, that I want to make here, is that these are the two simplest ways using MATLAB. One, using graphical methods. The second, using fzero. And fzero has two different options that we're using here. We can either give it 2 points, which is a bracketing method. We can use a single point or a single guess, and that's called a fixed point method or an open method in a more general case. And we're going to be looking at each of these in future lessons.